Now we will talk about something called dependent random choice. So we are learning about how to find a small graph H in a big graph G. And sometimes it's useful to use this terminology of embed or embedding. So we consider function which maps the vertices of H into vertices of G so that it is injective and it's graph homomorphism. Then the image of this, so this consists of the vertices and edges. So this is the subgraph of G, which is isomorphic to H. This means that finding a copy of H in G is same as finding this embedding of H into G. So this is graph embedding. And we use the terminology that the H embeds into G, meaning that the G contains a copy of H as a subgraph. So let's consider, we use this terminology of embedding partially because it's useful to describe the process of finding H in G. Oftentimes, when we have H and then H has vertices, B1 to say BH, and we have G, we want to find the vertex that plays the role of B1, another vertex that plays the role of B2. So we might want to find this one by one in a sequential way. And you can imagine this as you are embedding one vertex to here, and then next vertex to here, and next vertex to here. So you might thinking this as extending your partial embedding into a bigger partial embedding, and eventually to an embedding. So that gives us partial motivation to consider this as a embedding problem, graph embedding problem, and then you want to find this embedding. Let's consider H be a bipartite graph with a vertex partition X and Y. You have X and you have Y. All the edges are between. And let's say the vertices in X are like X1 to X H. And assume we want to embed these vertices before these vertices. So we embed X1 to XH into pi X1 to pi XH in order. Then once you finish embedding the vertices here, then now you start the embedding Y. One thing is that this X is an independent set. So as far as you embed this into some vertex, as far as they are all different, as far as they are all distinct, it is a legitimate embedding. So that's a legitimate partial embedding. So no, the bad case is if there is an edge and then you embed these two and then there are no edges between them, but that doesn't happen because X is an independent. Once we have that, then now you embed the vertices of Y into these vertices. But what do we have to do? when we embed vertices in Y, we want to make sure that Y embeds into, say, you take a neighborhood of Y. So in here, you have Y, then you consider its neighborhood. Let's say these three vertices. And you consider the image of these three vertices. And you take a common neighborhood in G of them. So if this Y is adjacent to, in here, Y is adjacent to, say, x1, x3, x7, then here, this is pi x1, pi x3, pi x7. As long as you embed Y into a common neighborhood of them, and it's okay. So that's what we want to do. Then what's the ideal situation? Ideal situation is that this set is large. That means there are many candidates for embedding Y. Ideally, it's even larger than the size of Y. Then what happens? So you take one vertex and then you embed into here. And then next Y, you want to embed it here, but you have to avoid the previous vertex that you chose. Let's say not just bigger than Y, say bigger than X plus Y. So when you embed Y into here, then you have this many choices, the choices in here. And among them, you have to exclude the choices that the previous vertices. It could be some vertices in Y, as well as some vertices in X, the image of X. You exclude them, and then still there are remaining ones, then you embed Y into here. But as long as this set is bigger than that, you will never run out of options. So let's say R is the maximum degree of the vertices in Y. The ideal situation is the following, that every R vertex of, say, some set U of size X has at least m common neighbors with m being larger than the number of vertices in Y. So this is the ideal situation. In such a case, what can you do? You just embed the vertices in X into U. You just map all the vertices in X to U. And then you order the vertices in Y, and then one by one you embed into the corresponding set, the common neighborhood of the image of its neighbor. Then this will complete the embedding of H, and then you find a copy of H in your graph G. Okay, then how can we ensure this? So this is the ideal situation. How can you find the sets of U? So in this lecture, we introduce what's called dependent random choice, which is the way to find such a good set U. So watch this. So let me write down this lemma. let's say you have a number A, B, M, N, R, and let G be on M vertex graph with average degree T. Okay, technically T does not have to be a natural number. I mean, real number is in case. And if there is T, natural number T that satisfies the following equation inequality, T to the T divided by N to the T minus 1 minus N choose R times M over N to the T is bigger than A. So you will see the meaning of this inequality in the proof of this lemma. But as long as that inequality holds, then you can find such a subset U. So there exists a subset U of vertices which has size at least A, such that every R vertices in U have at least M common neighbor. In G. So what do we want to do? We want to choose this vertex that U in a random way. But if we just choose a subset of R vertices uniformly random, then this does not, this does not hold. What do we want? So let's get the intuition. So U is here, and let's say you have some W1 R vertex. So it is an R set. So when I say R set, this is set of size R. And let's say you have another, like W2, another R set. What do we want? We want to choose this U in such a random way, in some sort of random way, to ensure that if this R vertices has lots of common neighbor, then we want it to be included more likely. So it's more likely to include, while if has a less number of common neighbor, we want it to be less likely to include. So if, say, the set of common neighbors of W1 is bigger than set of the number of common neighbor of W2, and we want W1 is included in U being more likely this happen more likely than this. And how can we do this? For this, one thing we can do is that we choose a random vertex B and let U be the neighborhood of B. Then what happens? And what's the probability? The probability that the W1 is included subset of U is is same as the probability that this B is chosen as a common neighborhood of this W1. And probability that the W2 is subset of U is the probability that the B is in a common neighborhood of this. And from our assumption, this is bigger. So this shows that the W1 is more likely to be a subset of U than W2. So this motivates the following proof. So as we get our intuition here, what we do instead is we don't choose just one random vertex, we choose several random vertex, and then we let U be the common neighborhood of them. So let's start the proof. For each I between 0, 1, and t, we choose a random vertex, bi, independently, uniformly, and random. So this is independent random trial, which means P1 and P2 could be the same vertex. So let's say A is the common neighborhood of this. If T vertices. And let's say X is the size of A. This is the random variable. Then we can compute the expectation of this. So what's the computation? So for each B, so let's say for each B, you can compute the probability that this B is in A. What's the probability? So B is in A is same as B1 to BT are all in the neighborhood of this B. So the probability of this is N over the size of neighborhood of B. That's for each BI, and then they are independent, so you take a T power. And what's this? This is over all vertices. So this is like N to the negative T times summation of the degree to the T. And use the convexity of this function. What do you do? This can be written as 1 minus, we can write it this way. And this is what? This is the average of the function of fx, which is x to the t. And that's a list. Like you take the average and then apply the function, which is what? If every degree was d, so you have d to the t and n to the t minus 1. So this is d. So you get this. Then what? Now what you can do is that curly R is a set of all R subsets, capital R, which has size R, small r, that has the common neighbor size is smaller than M. So this is collection of sets of size R with common neighborhood is small. And now we can introduce the random variable which counts the number of subsets R, which is included in A, such that its common neighborhood has size smaller. In a moment. Then this counts the number of R subsets of A, which is bad, and then we want to make sure that there are no such thing. For that, we compute the expectation. And what's this? For all such that S at R, the probability that each one of them is included in R is R is inside of this A if and only if all the B1 to BT are inside of common neighborhood of them. Then common neighborhood of B1 to BT contains this R. And then that's the probability here. But in fact, what do we know? Because this is small. This is bounded from the size of this curly R and times M over N to the T, which is M most, this. Then by linearity of expectation, we can compute the expected size of x minus y, which is d to the t over, at least d to the t over n to the t minus 1 minus n choose r times m over n to the t. And from our assumption, if it is exactly what we get here, that's at least A. Then what? This uses the deletion method, alteration method that we learned in the introduction to the graph theory course. It implies that there exists a choice of this x1 to b1 to be t, bt, which is a set A satisfying this inequality. We consider such a set A and what? Delete one vertex from each subset R, which lies inside A. And the resulting set U then it's at least what x minus y, which is at least A, and U is our desired set. So this finds what we want. Observe that this U is chosen in dependent way. We choose something else, which is B1 to BT, and the choice of U depends on its previous choice of B1 to BT. Hence, the name dependent random choice comes. So by using this, we achieve that the certain subsets are more likely to be included in U than some other sets. And by using this lemma, we can prove some theorems regarding the extremal numbers. And I will talk about that in the next video. Okay, I'll see you in the next video.